Welcome back, and now we are finishing the lecture series by Vladimir Dotsenko with the third lecture. No, the fourth one now. Yeah, and there will be the fifth after that.
Right. Yes. Yesterday we finished with the discussion of the Koszul complex of a quadratic algebra, and maybe somehow to create some connectivity between the stories. Well, first let me quickly recall the protagonist, the quadratic algebras we are thinking about, quadratic algebras related to Kuiper. So we take Kuiper Q and we look at this algebra AQ, which has generators A, I, K, where I is a vertex of the quiver and K is a non-negative integer, and this guy is of degree MII, so this is the number of loops at I plus 2K. Then we impose the relations, we impose the supercommutativity of these guys, and we impose the relations that I'm going to write in these for these generating series of AIKs. So AI of Z, AJ of W vanishes of order Mij at Z equal to W, which can be written as certain quadratic relations that we saw yesterday. And what I'm going to say, yesterday we saw in one particular example the Koszul dual algebra. Let me write the general formula for the Koszul dual, which will be in any case useful for us. And also in the Koszul complex, to construct it, we were constructing the tensor product of an algebra with the linear dual of the quadratic dual. And so I will also say it will be important for us, of crucial importance for us, how to compute the linear dual of this algebra. Because for an arbitrary quiver, it is difficult to describe a basis in this algebra, but it is easy to describe a basis in its linear dual. There is this kind of fun effect that enters a lot of arguments. And so
I have a question before you really start. What you wrote downstairs, like this AIZ, AJW vanishes at pointer Mij at Z equal W, it looks for me a lot like vertex operator algebras, this kind of stuff, or also CFT, so on physics side. Is it like of this flavor?
It is. So yes. Well, let me get back to your question in 5 minutes. So let me describe in full generality the Koszul dual algebra, and then I return to your question because it will become more pertinent at that point. Yes.
You mentioned linear dual of an algebra. What does that mean?
Well, I mean,
just dual as
a vector space. It's multigraded with finite dimensional graded component. They dualize component by component, so no funny business going.
I understand. Okay.
Right. So this description of the quadratic dual. So the quadratic dual is generated by guys that I'm going to call B ik, which really just you can think of it as the dual basis of AIKs, but relations. So somehow I want to emphasize that it will be convenient for us to think that relation AQ is a supercommutative algebra. We know that the quadratic dual of a supercommutative quadratic algebra is a universal enveloping of a Lie superalgebra, so I will write relations as supercommutators. And in these supercommutators, it will be implied that the parity of these guys is opposite to the parity of AIKs, because Koszul duality changes sort of parity of generators.
I'm sorry, and then the parity is is MII, the number of loops?
Yes, that's right. Okay, that's right. And the relations, for I different from J, I will write some relations, just some linear combinations of supercommutators, and then I'll momentarily say how to think about these generators, because if you just look at these combinations of anti-commutators or supercommutators, they don't really tell you what they want to communicate here. So for I different from J, you have a sum from P equal to 0 to Mij minus 1 to the power P, binomial coefficient Mij choose P, and the bracket of B I K minus P B L J plus P equal to 0, and you impose these relations for all K greater than or equal to Mij and all L greater than or equal to 0. Then, if I is equal to J, there is one little pesky annoying case of MII equal to 0 vertex with no loops. It's a little bit special, different from others. You just say that BIKBIL is equal to 0. I emphasize that since all parities are opposite, this means that these guys are both odd, and so this commutator is really an anti-commutator. So all these commutators are supercommutators. In particular, this guy is necessarily an anti-commutator. And if MII is bigger than 0, then the formula is a little bit quite similar. P equal to 0 to MII minus 1 to the power P, MII minus 1 choose P, BIK minus P, BIL plus P equal to 0, and all K greater than or equal to MII minus 1, L greater than or equal to 0. So now, what do these relations want to tell us, really? Because you look at them like that, it's not so clear what they want to say. So these relations can be thought of as follows. Take BI of Z equal to sum BI Z to the power I, except for I'm going to take, even though I only bik z to the power k, and I'm going to take the sum over all integer k, except for I don't really have generators with negative indices. But let me pretend for a second that somewhere in some alternate universe they exist, right? And then, so for example, this relation star wants to say the following, that I take the commutator bi of z with bj of w, I multiply it by z minus w to the power mij, and I say that it is equal to 0, and then this is many relations. I have the coefficient at each power, at each monomial z to the power k, w to the power l. And now I remember that I don't really have bi's with negative indices, so I extract only relations that actually make sense, only relations in which everything is with non-negative indices. And so extract only relations that make sense. And this will give you precisely these relations there. Similarly, in this case, you just have the exponent mi minus 1. And then, so where I'm ready to comment on the question of Piotr, because so this is kind of the locality relations in the vertex operator context. So that's certainly is something that I guess everyone in this room probably would have seen somewhere one way or the other. And this is in a sense, one way to think about it, that the algebra AQ star is related to the free vertex to the universal envelope of the free vertex Lie algebra for the locality MQ minus identity, where M is the incidence matrix of the quiver. What do I want to say? So, in the context, so in general, so when we work with sort of more classical algebraic structure, associative algebras, Lie algebras, there is the notion of a free object, right? Free Lie algebra, free associative algebra. In the context of vertex algebras, there is this locality condition, so somehow you cannot just say free vertex algebra generated by something, because the locality conditions, they are part of the what describes the structure. But once you say what kind of locality properties the generators satisfy, you can talk about free vertex Lie algebras and so on, and this is exactly what is happening. So you take some currents, you say that that they are mutually local with the corresponding exponents, and voilà. Now, when I say, so what is hidden in the words related to? So I wasn't intentionally a bit vague here. So first of all, this is so this algebra, it's an honest associative algebra, or if you think universal developing of an honestly algebra, there is nothing vertex here. So first of all, once you have a vertex algebra, you can pass to an honest algebra, which is called the algebra of coefficients of the vertex algebra. So second, the algebra of coefficients always have some kind of decomposition into its positive and negative part, which somehow are they're at least formally defined in a very different way. So the positive part is sort of in something much more concrete, the negative part is a bit indirect. And so somehow this thing, what I told you, extract only relations that make sense, that's exactly what defines the positive part of the coefficient algebra. And so this is the relationship to one relationship to vertex algebra. So now, of course, then you're right that these conditions of vanishing of certain order, it also appears in various situations related to vertex algebras, and so in fact, one can I would say that the reasonable way to think about it is that I am telling you some story about Koszul duality where I'm using sort of supercommutative algebras and Lie superalgebras, but somehow these stories are somehow some shadow of some Koszul duality story on the level of vertex algebras, and so there is this commutative vertex algebra and vertex Lie algebra, and so some sort of Koszul duality between them. And sadly, it's not something that actually is systematically developed in the literature, and for that reason, I guess I will leave that as a speculation, and will tell you the story that doesn't touch the vertex algebra story too much. Right. Yes, and so this is the description of the Koszul dual, and let me very quickly tell you how to compute the linear dual of AQ, because this is it will be very useful for us in any case. Yes.
If I write OP for B, it will be singular at the level of Mij. And OP for A is Z minus I to the power of Mij. So this means I can put minus in behind Mij, and that's it. Sending Mij to minus Mij will send me to the dual?
No, it's well.
And parity.
Yes, so the OPE, yeah, maybe that's what it means. So the OPE of B, it has a pole of suitable order, and the OPE of A has a zero of suitable order, and the point that these orders match, and that's why the Koszul duality happens, right? So okay, so description of a Q linear dual. So the story is very so here it will be beneficial to remind ourselves that so as I was saying, a Q is general is infinite dimensional. We're going to split it into finite dimensional pieces and dualize piece by piece. And so what are the gradings here? So there is this grading by the degree that is described here, and there is also grading by the x by the product of many copies of integers corresponding to the vertices. So I'm just saying that, so I'm going to say that extra grading by, I don't know, z to the power vertices of the quiver, where each aik has degree ei, the ith basis vector of this lattice. So then I'm going to dualize. So I fix this multi-degree, and I'm going to then I still have the degree that we had before, but now, so if I fix D, this AQD is a singly graded vector space, and then I'm going to dualize that degree by degree, and it turns out that it has a very elegant description. It turns out that, so let's say fact AQD dual is naturally identified with so I'm going to take the polynomial, so up to some factor, it is going to be the space of appropriate multisymmetric polynomials that feature in the shuffle product description of the homological whole algebra. So I'm going to take Zij, where I is a vertex of the quiver, J is between 1 and D I, and I'm going to take the product of the symmetric groups as D1, as D M, well, where I suppose M is the number of the vertices, and then I'm going to multiply it by something, and there will be two products. There will be a product for I different from J and for I's, and the first will be R prime di Z I R minus Z I R prime to the power MII, and then the product 1 less than R less than VI, 1 less than R prime less, well, let me call this I prime perhaps, d I prime Z I R minus Z I prime R prime M I prime. So somehow it's, so if you have just one vertex, then it will be just some power of the van der Waals determinant, and this is some kind of something, some generalized, yeah. In any case, so this dual is naturally identified with this. And since I wrote the word naturally, well, at least that I should justify for you, right? And so what is natural? Okay, so namely, if we have some linear function psi in a QD linear dual, we associate to it the following thing. You pair this linear function with the product over all vertices of the quiver, and then for R between 0 and di, ai of z I r. Right, so you have these currents, the generating functions for the generators of your algebra. You use all these variables as the arguments, so that was depending on z. Then I use instead of z all these formal variables. And so I have the thing which is now a power series in all these variables z, whose coefficients are products of generators. And so I can, this psi eats products of generators. So I am left a priori with a power series. And now I am claiming that it's not quite a power series, but a polynomial, and not just a polynomial, but symmetric polynomial vanishing on diagonals of certain orders. And so why is it a polynomial? The polynomial is because we dualize degree by degree, so this psi is supported at finitely many degrees in total. That is okay. Symmetric, well, vanishing on, so it will be, so these generators, they supercommute. So in general, this polynomial will be appropriately symmetric / antisymmetric in various groups in each group of variables. That is also clear. Also, we have these relations that say that products vanish of certain order. And this vanishing of certain order will ensure all these divisibilities. And then, if MII is odd, this kind of power of Vandermonde will be antisymmetric, so after we divide by what remains will be an honestly symmetric polynomial. And then you need some little argument saying that each psi can be obtained this way, but this is not a very difficult argument. So, but at least I hope I convinced you that I am justified using the word naturally, because it's a very natural construction. So generally, this construction people often refer to as functional realization of a Q star. And so in the particular case of the quiver with one vertex, two loops, the corresponding thing was studied long before any kind of Koch business. It was studied in the context of representations of SL2 hat by Fagin and Steinovsky in early 90s, and so they call, in that particular case, they call this functional realization, and so I would prefer to give credit to that wonderful idea by calling, by using it, this terminology in general. Right, okay. Now, perhaps at the remaining piece of the board, I'm going to formulate a little exercise, which is open-ended, because I haven't really tried very carefully to solve this exercise myself, so it's not a learning exercise. It's more kind of possibly difficult open problem exercise. So now we have. And so in the formula for the Koszul complex, we have some degree of freedom which algebra to choose for A and which for quadratic dual, because the quadratic duality is an involution. So let's consider the Koszul complex AQ quadratic dual tensor AQ linear dual. So here we need to take one algebra and its quadratic dual linear dual. I make this choice because I just explained to you that linear dual has this lovely description. And the question is to describe explicitly or sufficiently explicitly the Koszul differential and try to directly compute, try to directly check the Koszul complex is acyclic, that its homology is concentrated in degree 0, which will give a proof of Koszulness of this algebra. Describe explicitly can show that homology is concentrated in degree.
Is it not known that these algebras are Koszul in general?
It is known. It is known, but yeah, I will definitely give at least a sketch of the proof of the Koszul property. So this essentially the proof of Koszulness of this algebra. It's the main result of the paper that myself, Evgeny Feigin, Piotr, and Markus Reinecke wrote a few months ago. Yes, but our argument is very different, and in principle, I don't know. It would be interesting, especially some complexes of that kind of nature one can interpret from the vertex operator viewpoint. So perhaps proving that homology is constrained to degree 0, for example, perhaps if you want computing the contracting homotopy, you can find it sort of also of some vertex operator nature. So in principle, it's not impossible that this also works, but I don't think that anyone ever tried very systematically. Okay, I started at what time?
Okay, started, let's say, 10 past, so till 55.
Okay, good. Yes, so now I suppose I will say a few words about the general. So we already discussed some ways of proving Koszulness, and I will now say a few words about the PBW basis method, and then we will be able to take a short break, and after that we will continue. So in general, so there is the there is method to work with commutative algebras, not necessarily commutative algebras, much more general than the PW basis story, the method using what is called Grobner bases. And I will very quickly say how to think about that. When we work with algebras presented by some generators and relations, this means that we fix some generators so we can talk about monomials. Relations are linear combinations of monomials. Grobner basis, it's a non-linear version of Gaussian elimination. So you order monomials and you say that each relation has the leading monomial that you want to eliminate and the others that you use as the lower terms that you use to rewrite that eliminated monomials. So you choose, and I will coherently an ordering of monomials. And coherently means that I want this ordering to be compatible with products. So if a monomial A is less than a monomial B, then AC is less than BC. So I can multiply inequalities by monomials. Yes, and then so then each relation has a leading monomial and can be used for rewriting leading monomials. That monomial as a sum of lower terms. And somehow we say that relations form a Grobner basis if monomials that cannot be rewritten, monomials, non-simplifiable monomials, form a basis in your algebra. Let me maybe give a silly example showing that it's a very non-empty condition, that usually there are some hidden relations, that hidden things that you don't see like that. So suppose that we have generators x, y, and z, and relations xy equal to 1 and yz equal to 1. Then, of course, well, I didn't tell you what possible coherent orderings are, but here it is clear that it's only logical to direct our writing like that, to replace xy by 1, because if we can replace 1 by xy, then it will be just exploding and without any end to it, so it's not really a practical thing to do. So we can rewrite xy into 1 and yz into 1. But then, if we have xyz, we can rewrite it in two different ways, right? We can rewrite it into z, and we can rewrite it into x. Here I replace xy by 1 or yz by 1. And so, using our relations, we can prove that in our algebra z is actually equal to x, which is, if you think of it, not very surprising. This is what we teach students in undergraduate algebra courses, that if an element has a left inverse and the right inverse, then those two inverses are equal to each other. This is precisely what I just proved here. But both z and x are non-simplifiable. You cannot rewrite them, you cannot replace, you don't have occurrences of either xy or yz. And so you have two non-simplifiable monomials which are equal in the algebra, so clearly non-simplifiable monomials do not form a base in this instance. So non-simplifiable, so no basis of non-simplifiables. So it's not a real condition, most certainly. Now, how does it help with Koszul algebras? Yes, 5 minutes is exactly what I need. So suppose A is an algebra with quadratic relations. So there is a fact if for some ordering of monomials the relations of the quadratic relations of A form a Grobner basis, then A is necessarily a Koszul algebra. In this case, the non-simplifiable monomials are said to be a PBW basis of A. Form the basis of A, which is all quite great because, well, after the break I will explain that this thing is a condition that you can directly verify. So finally we have something which is verified by more or less a simple finite calculation. A warning is this is sufficient but not necessary. There exist quadratic algebras that are Koszul but don't have Grobner basis for any ordering of variables, and the classical example, which is customary to give here, is the example of the so-called three-dimensional Sklenin algebras. if you take three generators x, y, z, and relations xy minus yx equal to z squared, yz minus zy equal to x squared, zx minus xz equal to y squared, this algebra is Koszul, but the Koszul property cannot be proved by this criterion. So it's a nice condition, but it still has its limitations. All right, I think it's a good moment to stop, and then we'll continue after the break.
Questions? Okay, so maybe let's have our break. So we'll start 10 past.
Okay. You probably want to stop the recording?
Yeah, I should stop the recording. Thanks for the reminder. I mean, we would just have 15